just a technology marvel. And they turn into these switches. Our InfiniBand switch, the silicon is working fantastically. Second half of this year, we will ship the silicon photonics switch in the second half of this year. In the second half of next year, we'll ship the Spectrum X. Because of the MRM choice, because of the incredible technology risks that over the last 5 years that we did, and filed hundreds of patents, and we've licensed it to our partners so that we can all build them, now we're in a position to put silicon photonics with co-package options, no transceivers, fiber, direct fiber into our switches with a radix of 512. This is the 512 ports. This would just simply not be possible any other way. And so this now set us up to be able to scale up to these multi-100,000 GPUs and multi-million GPUs. And the benefit, just so you imagine this is incredible. In a data center, we could save tens of megawatts. Let's say 10 megawatts, well, let's say 60 megawatts. 6 megawatts is 10 Rubin Ultra racks. 6 megawatts is 10 Rubin Ultra racks, right? And 60, that's a lot. 100 Rubin Ultra racks of power that we can now deploy into Rubins. All right, so this is our roadmap. Once a year, an architecture every 2 years, a new product line every single year, X factors up, and we try to take silicon risk or networking risk or system chassis risk in pieces so that we can move the industry forward as we pursue these incredible technology. Vera Rubin, and I really appreciate the grandkids for being here. This is our opportunity to recognize her and to honor her for the incredible work that she did. Our next generation will be named after Feynman. Okay, NVIDIA's roadmap. Let me talk to you about enterprise computing. This is really important. In order for us to bring AI to the world's enterprise, first we have to go to a different part of NVIDIA. The beauty of Gaussian splats. Okay, in order for us to take AI to enterprise, take a step back for a second and remind yourself this. Remember, AI and machine learning has reinvented the entire computing stack. The processor is different, the operating system is different, the applications on top are different. The way the applications are different, the way you orchestrate it are different, and the way you run them are different. Let me give you one example. The way you access data will be fundamentally different than the past. Instead of retrieving precisely the data that you want and you read it to try to understand it, in the future, we will do what we do with Perplexity. Instead of doing retrieval that way, I'll just ask Perplexity what I want. Ask it a question, and it will tell you the answer. This is the way enterprise IT will work in the future as well. We'll have AI agents, which are part of our digital workforce. There's 1 billion knowledge workers in the world. There are probably going to be 10 billion digital workers working with us side by side. 100% of software engineers in the future, there are 30 million of them around the world, 100% of them are going to be AI assisted. I'm certain of that. 100% of NVIDIA software engineers will be AI assisted by the end of this year. And so AI agents will be everywhere. How they run, what enterprises run, and how we run it will be fundamentally different. And so we need a new line of computers. And this is what started it all. This is the NVIDIA DGX-1. 20 CPU cores, 128 gigabytes of GPU memory, 1 petaflops of computation, $150,000, 3,500 watts. Let me now introduce you to the new DGX. This is NVIDIA's new DGX, and we call it DGX Spark. DGX Spark. Now you'll be surprised. 20 CPU cores. We partnered with MediaTek to build this for us. They did a fantastic job. It's been a great joy working with Rick Tsai and the MediaTek team. I really appreciate their partnership. Built us a chip-to-chip NVLink CPU to GPU. And now the GPU has 128 gigabytes. And this is fun. 1 petaflops. So this is like the original DGX1 with PIM particles. You would have thought that that's a joke that would land at GTC. Okay, well, here's 30 million, there are 30 million software engineers in the world, and it's, 10, 20 million data scientists. And this is clearly the gear of choice. Thank you, Jenny. Look at this. In every bag, this is what you should find. Right? This is the development platform of every software engineer in the world. If you have a family member, spouse, somebody you care about who's a software engineer or AI researcher or just data scientist, and you would like to give them, you know what, the perfect Christmas present. Tell me this isn't what they want, huh? And so, ladies and gentlemen, today we'll let you. We will reserve the first DGX Sparks for the attendees of GTC. So go reserve yours. You already have one of these, so now you just got to get one of these. All right, the next. Thank you, Janine. The next one is also a brand new computer, one that the world's never had before. So we're announcing a whole new line of computers. This is a new personal computer, a new personal workstation. I know, it's crazy. Check this out. Grace Blackwell, liquid cooled. This is what a PC should look like. 20 petaflops. Unbelievable, 72 CPU cores, chip-to-chip interface, HBM memory, and just in case, some PCI Express slots for your GeForce. Okay, so this is called DGX Station. DGX Spark and DGX Station are going to be available by all of the OEMs. HP, Dell, Lenovo, Asus. It's going to be manufactured for data scientists and researchers all over the world. This is the computer of the age of AI. This is what computers should look like. And this is what computers will run in the future. And we have a whole lineup for enterprise now, from little tiny one to workstation ones, the server ones to supercomputer ones, and these will be available by all of our partners. We will also revolutionize the rest of the computing stack. Remember, computing has 3 pillars. There's computing, you're looking at it. There's networking, as I mentioned earlier, Spectrum X going to the world's enterprise, an AI network. And then third is storage. Storage has to be completely reinvented. Rather than a retrieval-based storage system, it's going to be a semantics-based retrieval system, a semantics-based storage system. And so the storage system has to be continuously embedding information in the background, taking raw data, embedding it into knowledge, and then later when you access it, you don't retrieve it, you just talk to it. You ask it questions, you give it problems. And one of the examples, I wish we had a video of it, but Aaron at Box even put one up in the cloud, worked with us to put it up in the cloud. And it's basically, a super smart storage system. And in the future, you're going to have something like that in every single enterprise. That is the enterprise storage of the future. And we're working with the entire storage industry, really fantastic partners, DDN and Dell and HP Enterprise and Hitachi and IBM and NetApp and Nutanix and Pure Storage and VAST and Weka. Basically, the entire world storage industry will be offering this stack. For the very first time, your storage system will be GPU accelerated. And so somebody thought I didn't have enough slides. And so Michael thought I didn't have enough slides. So he said, Jensen, just in case you don't have enough slides, can I just put this in there? And so this is Michael's slides. But he sent this to me. He goes, just in case you don't have any slides. And I got too many slides. But this is such a great slide. And let me tell you why. In one single slide, he's explaining that Dell is going to be offering a whole line of NVIDIA enterprise IT AI infrastructure systems and all the software that runs on top of it. Okay, so you can see that we're in the process of revolutionizing the world's enterprise. We're also announcing today this incredible model that everybody can run. And so I showed you earlier R1, a reasoning model. I showed you versus Llama 3, a non-reasoning model. And obviously R1 is much smarter. But we can do it even better than that. And we can make it possible to be enterprise ready for any company. And it's now completely open source. It's part of our system we call NIMS. And you can download it. You can run it anywhere. You can run it on DGX Spark. You can run it on DGX Station. You can run it on any of the servers that the OEMs make. You can run it in the cloud. You can integrate it into any of your agentic AI frameworks. And we're working with companies all over the world, and I'm going to flip through these, so watch very carefully. I've got some great partners in the audience. I want to recognize Accenture, Julie Sweet and her team are building their AI factory and their AI framework. Amdocs, the world's largest telecommunications software company. AT&T, John Stankey and his team building an AT&T AI system, agentic system. Larry Fink and BlackRock team building theirs. Anirudh. In the future, not only will we hire ASIC designers, we're going to hire a whole bunch of digital ASIC designers from Anirudh Cadence that will help us design our chips. And so Cadence is building their AI framework. And as you can see, in every single one of them, there's NVIDIA models, NVIDIA NIMs, NVIDIA libraries integrated throughout so that you can run it on-prem, in the cloud, any cloud. Capital One, one of the most advanced financial services companies in using technology, has NVIDIA all over it. Deloitte, Jason and his team, EY, Janet and his team, NASDAQ, and Adina and her team, integrating NVIDIA technology into their AI frameworks, and then Christian and his team at SAP, Bill McDermott and his team at ServiceNow. That was pretty good, huh? First, this is one of those keynotes where the first slide took 30 minutes, and then all the other slides took 30 minutes, all right? So next, let's go somewhere else. Let's go talk about robotics, shall we? Let's talk about robots. Well, the time has come for robots. Robots have the benefit of being able to interact with the physical world and do things that otherwise digital information cannot. We know very clearly that the world has severe shortage of human laborers, human workers. By the end of this decade, the world is going to be at least 50 million workers short. We'd be more than delighted to pay them each $50,000 to come to work. We're probably going to have to pay robots $50,000 a year to come to work. And so this is going to be a very, very large industry. There are all kinds of robotic systems. Your infrastructure will be robotic. Billions of cameras in warehouses and factories, 10, 20 million factories around the world. Every car is already a robot, as I mentioned earlier, and then now we're building general robots. Let me show you how we're doing that. Everything that moves will be autonomous. Physical AI will embody robots of every kind, in every industry. 3 computers built by NVIDIA enable a continuous loop of robot AI simulation, training, testing, and real-world experience.
Training robots requires huge volumes of data. Internet-scale data provides common sense and reasoning, but robots need action and control data, which is expensive to capture. With blueprints built on NVIDIA Omniverse and Cosmos, developers can generate massive amounts of diverse, synthetic data for training robot policies. First, in Omniverse, developers aggregate real-world sensor or demonstration data according to their different domains, robots, and tasks. Then use Omniverse to condition Cosmos, multiplying the original captures into large volumes of photoreal, diverse data. Developers use Isaac Lab to post-train the robot policies with the augmented dataset. And let the robots learn new skills by cloning behaviors through imitation learning, or through trial and error, with reinforcement learning AI feedback. Practicing in a lab is different than the real world. New policies need to be field tested. Developers use Omniverse for software and hardware-in-the-loop testing, simulating the policies in a digital twin with real-world environmental dynamics, with domain randomization, physics feedback, and high-fidelity sensor simulation. Real-world operations require multiple robots to work together. Mega, an Omniverse blueprint, lets developers test fleets of post-trained policies at scale. Here, Foxconn tests heterogeneous robots in a virtual NVIDIA Blackwell production facility. As the robot brains execute their missions, they perceive the results of their actions through sensor simulation, then plan their next action. Mega lets developers test many robot policies, enabling the robots to work as a system, whether for spatial reasoning, navigation, mobility, or dexterity. Amazing things are born in simulation. Today, we're introducing NVIDIA Isaac GR00T N1. GR00T N1 is a generalist foundation model for humanoid robots. It's built on the foundations of synthetic data generation and learning in simulation. GR00T N1 features a dual system architecture for thinking fast and slow, inspired by principles of human cognitive processing. The slow thinking system lets the robot perceive and reason about its environment and instructions, and plan the right actions to take. The fast thinking system translates the plan into precise and continuous robot actions. GR00T N1's generalization lets robots manipulate common objects with ease and execute multi-step sequences collaboratively. And with this entire pipeline of synthetic data generation and robot learning, humanoid robot developers can post-train GR00T N1 across multiple embodiments and tasks across many environments. Around the world, in every industry, developers are using NVIDIA's 3 computers to build the next generation of embodied AI.
Physical AI and robotics are moving so fast. Everybody pay attention to this space. This could very well likely be the largest industry of all. At its core, we have the same challenges. As I mentioned before, there are 3 that we focus on. They are rather systematic. 1, how do you solve the data problem? How, where do you create the data necessary to train the AI? 2, what's the model architecture? And then 3, what's the scaling laws? How can we scale either the data, the compute, or both, so that we can make AIs smarter and smarter and smarter? How do we scale? And those fundamental problems exist in robotics as well. In robotics, we created a system called Omniverse. It's our operating system for physical AIs. You've heard me talk about Omniverse for a long time. We added 2 technologies to it. Today I'm going to show you 2 things. One of them is so that we could scale AI with generative capabilities. A generative model that understands the physical world. We call it Cosmos. Using Omniverse to condition Cosmos, and using Cosmos to generate an infinite number of environments allows us to create data that is grounded, controlled by us, and yet be systematically infinite at the same time. Okay, so you see Omniverse, we use candy colors to give you an example of us controlling the robot in the scenario perfectly, and yet Cosmos can create all these virtual environments. The second thing, just as we were talking about earlier, one of the incredible scaling capabilities of language models today is reinforcement learning, verifiable rewards. The question is, what's the verifiable rewards in robotics? And as we know very well, it's the laws of physics. Verifiable physics rewards. And so we need an incredible physics engine. Well, most physics engines have been designed for a variety of reasons. They could be designed because we want to use it for large machineries, or maybe we design it for virtual worlds, video games and such. But we need a physics engine that is designed for very fine-grained, rigid and soft bodies, designed for being able to train tactile feedback and fine motor skills and actuator controls. We need it to be GPU accelerated so that these virtual worlds could live in super linear time, super real time, and train these AI models incredibly fast. And we need it to be integrated harmoniously into a framework that is used by roboticists all over the world, Mujoko. And so today we're announcing something really, really special. It is a partnership of 3 companies: DeepMind, Disney Research, and NVIDIA, and we call it Newton. Let's take a look at Newton. Tell me that wasn't amazing. Hey, Blue. How are you doing? How do you like your new physics engine? You like it, huh? Yeah, I bet. I know. Tactile feedback, rigid body, soft body simulation, super real time. Can you imagine just now what you were looking at is complete real-time simulation? This is how we're going to train robots in the future. Just so you know, Blue has 2 computers, 2 NVIDIA computers inside. Look how smart you are. Yes, you're smart. Okay. All right. Hey, Blue, listen. How about let's take them home? Let's finish this keynote. It's lunchtime. Are you ready? Let's finish it up. We have another announcement. You're good. You're good. Just stand right here. Stand right here. Stand right here. All right, good. Right there. That's good. All right, stand. Okay, we have another amazing news. I told you the progress of our robotics has been making enormous progress. And today we're announcing that Groot N1 is open sourced. I want to thank all of you to come Let's wrap up. I want to thank all of you for coming to GTC. We talked about several things. One, Blackwell is in full production, and the ramp is incredible. Customer demand is incredible, and for good reason. Because there's an inflection point in AI, the amount of computation we have to do in AI is so much greater as a result of reasoning AI and the training of reasoning AI systems and agentic systems. Second, Blackwell NVLink 72 with Dynamo is 40 times the performance, AI factory performance of Hopper. And inference is going to be one of the most important workloads in the next decade as we scale out AI. Third, we have an annual rhythm of roadmaps that has been laid out for you so that you could plan your AI infrastructure. And then we have three AI infrastructures we're building. AI infrastructure for the cloud, AI infrastructure for enterprise, and AI infrastructure for robots. We have one more treat for you. Play it. Thank you, everybody. Thank you for all the partners that made this video possible. Thank you, everybody that made this video possible. Have a great GTC. Thank you. Hey, Blue. Let's go home. Good job. Good little man. Thank you. I love you too. Thank you.